So
Great.
here we go.
Oh, fantastic. So hello, everyone. I'm going to do a very short about me. So I'm going into my fourth and final year at the University of Toronto. I'm studying a specialist in planetary science with a major in archaeology, and I'm also minoring in math. So throughout my academic journey so far, I have been very fortunate to work alongside brilliant mentors and colleagues who have inspired and guided me. And again, thinking retrospectively, the experiences that I have had with data collection and analysis in Turkey would end up significantly humbling me and motivating me to explore the developments and insights and what we gain from studying our own planet and the travesties within and how they can be applied to the study of celestial bodies. So this is something that means quite a lot. I'm very happy to share this with everyone. So I would like to do a very quick land acknowledgement from Toronto, as it is customary, to express my gratitude towards working and living on this beautiful earth. So I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and I am grateful to have the opportunity to work on this land. So we do this at the University of Toronto frequently because the Indigenous community at the University of Toronto is very prevalent, and they do a lot of great work for us, and it is very important to acknowledge this in every presentation that we give. So today I will be showcasing the exploration of celestial tremors and their profound implications for our understanding of the universe. So seismology is the study of seismic waves and their sources. It has been traditionally focused on Earth. However, with recent advancements in technology and space exploration, they have provided us with unprecedented opportunities to expand our knowledge beyond our home planet. So by studying seismology in extraterrestrial settings, we can unlock hidden secrets about the geophysical processes and history of celestial bodies. So the significance of understanding celestial tremors cannot be overstated, as it enables us to understand more about the formation, the geological evolution, potential habitability of that planet. So in the past decade, technological breakthroughs in space missions have revolutionized our ability to study seismology beyond Earth. So instruments like the Seismic Experiment for Interior Structure, or SEIS, on NASA's Mars InSight lander, which I will talk further about later on in my presentation, and planned missions such as Artemis for Lunar Seismology have paved the way for new discoveries and advancements in this field. So seismology is the scientific discipline that focuses on the study of seismic waves. They are vibrations that continuously propagate through the Earth or other celestial bodies in response to an energy release, such as earthquakes. So we use this data to then understand more about the structure, the composition, and dynamics of that particular body. So the identification of seismic events, such as Mars quakes or moon quakes, as we like to call them, allows for the investigation of subsurface processes. So seismic events can occur at different you move into the Earth due to the changing temperature and fluidity of the medium that you are in. So the variety of the materials influences the behavior of the seismic waves, and since they encounter different densities, elastic properties, and chemical compositions, this results in variations in wave velocities and transmission characteristics. So layered structured bodies like the Earth possess almost distinct boundaries and transition between different materials and physical states. So seismic waves can reflect, refract, and attenuate at these interfaces, leading to complex wave interactions altering their propagation paths. So seismic study these reflections and refractions to infer the presence, the thickness, and properties of various. So also an absence of an atmosphere leads to the reduced wave attenuation, resulting in longer travel distances for some seismic waves and potential interference with reflected waves. Next, I will be elaborating a little bit more on plane waves in seismology. So before delving into the extraterrestrial, I will use the Earth to define the basic understanding of seismicity and how waves propagate through different mediums. So pertaining to propagations, a plane wave is a theoretical wavefront that extends infinitely in all directions and travels in a straight line. So this is what seismologists use to have a solid foundation and understanding of wave directions. Plane waves exhibit properties such as wavelength, amplitudes, and directions of propagation. So when they approach the surface of the Earth, it encounters various layers with different properties, including density, elasticity, and composition, as I previously stated. So depending on the differences in the properties of the adjacent layers, the plane wave can undergo these processes such as reflection, refraction, and transmission. So specifically, reflection occurs when the wave is bounced back from the interface, while refraction refers to the bending of the wave as it crosses the interface. Transmission, on the other hand, refers to the passage of the wave through the interface into the next layer. So when these plane waves reach the surface of a body, it can generate surface waves, and those travel along the interface between the solid or fluid medium of the body and the surrounding medium, such as the atmosphere or the vacuum of space. So next we have earthquakes. So this is just pertaining to the earthquakes and the waves that are formulated when the earthquake occurs. So these different types of seismic waves are generated, and these are caused by a natural phenomena that occur when there is a sudden release of energy in the Earth's crust. So this is resulting from seismic waves that propagate through the ground. These seismic waves carry valuable information about the earthquake's source and Earth's internal structure. So the first type of seismic wave we encounter during an earthquake is called a P wave, also known as the primary waves or compressional waves. So P waves are the fastest waves and can travel through both solids and fluids. They have several distinct characteristics. So first, they cause particles in the ground to move in the same direction as the wave propagation. This results in a very back and forth motion, which is seen on the graph on the top left of your screen. That is just a visualization of P waves versus the other waves as well. So secondly, P waves, secondly, the P waves, they compress and expand the material as they pass through it. So think about it like a slinky, how it compresses and stretches as it moves through the Earth. So P waves also have the ability to travel through the Earth's layers, including the liquid outer core. So that's very, very cool. The next type of seismic wave is the S waves. So they are known as the secondary or shear waves. And these waves are slower than the P waves and can only travel through solids. They exhibit different characteristics compared to that of P waves. They cause particles in the ground to move perpendicularly to the wave propagation, resulting in a side-to-side or up and down motion. So unlike P waves, S waves cannot travel through fluids or the Earth's outer core. So both P waves and S waves are examples of body waves, which are waves that travel through the Earth's interior. So they interact with the various layers of the Earth and give us valuable information about the body's composition and structure. So next we have seismology beyond the Earth, finally. So challenges and opportunities. So seismology, traditionally focused on studying seismic waves on Earth, is now venturing beyond our home planet. So seismology beyond Earth involves the study of seismic activity and the behavior of seismic waves on celestial bodies such as planets, moons, and even asteroids, which is super exciting, and I will talk all about that very soon. Seismology beyond Earth presents unique challenges that set it apart from studying seismic activity on our planet. So let's explore some of these challenges together. Primarily, we have limited data availability. This is a very important thing that we cannot really grasp just yet, and it's the obtaining the seismic data from extraterrestrial bodies is a very significant challenge due to the limited number of missions equipped with seismometers. So data collection may be limited in terms of duration, spatial coverage, and the number of seismic events that are recorded. There are also issues with different geological compositions. So celestial bodies have diverse geological compositions. They range from rocky planets to icy moons, moons, which can significantly impact the behavior of the seismic wave. So it's not going to be very consistent, especially pertaining to what we have on Earth. And understanding how these seismic waves propagate through these materials requires adaptation of traditional seismological models and analysis techniques. Lastly, we have complex wave interactions. So again, very different from Earth. Seismic waves interact with layers, boundaries, and subsurface structures in very, very complex ways, leading to extremely complex math, which I could talk about, but I really don't want to for both the sake of time and the sake of your sanity, leading to very profound issues in the reflections, refractions, and scattering of these particles. It's very dense, to put it plainly. These interactions pose challenges in accurately interpreting the seismic data and extract meaningful information about the interior of celestial bodies. So despite these challenges, however, seismology beyond Earth presents remarkable opportunities for expanding our understanding of the universe. So some of these opportunities include studying planetary processes, super duper important. Seismic activity on celestial bodies reveals vital information about the geological processes such as tectonic activity, volcanic eruptions, and impacts. And understanding these processes helps us to comprehend the geological history and dynamics of these environments. As well, we can advance our comparative planetology. So comparing seismic activity and the properties of celestial bodies allows us to draw connections and identify the similarities or differences between them. So this comparative approach contributes to a broader understanding of the formation and evolution of planetary systems. Very cool stuff. Next, I'm going to talk a little bit more about the Mars InSight mission. So, hallelujah. Launched by NASA in 2018, they have provided unprecedented opportunities to study the seismic activity on Mars. So let's go into more of the significance of this. The Mars InSight mission's primary objective is to investigate the deep interior of Mars and shed light on the planet's geologic evolution. So the InSight lander, equipped with advanced instruments including the Seismic Experiment for Interior Structure, as I previously said, SEIS, has been studying Mars's seismic activity to understand the internal structure of Mars. The Seismic Experiment for Interior Structure is a state-of-the-art seismometer deployed by the Mars InSight mission, playing a pivotal role in studying the seismic waves of Mars. So the seismic data collected by the Mars InSight mission is of immense importance to the field of extraterrestrial seismology. And essentially, this is why, again, the Martian interior is, we don't know a lot about it, so this will obviously help us understand the geological composition. And since we know that it's a very geologically active planet, studying its seismic activity allows us to gain the insights into the composition and the movement of the waves through those mediums, which we do want to know more about. Also, with the comparative planetology is very important. Mars is very close to us, and there's a lot that we can do in terms of comparing these graphs one to the other, and it will help us enhance our understanding of the fundamental principles that govern planetary formation and evolution, especially within our solar system. As well, this gives us insight into planetary habitability. Very cool. Seismic data from Mars provides valuable information about the subsurface conditions and potential habitability of Mars. So understanding the geological environment and identifying the regions with stable subsurface conditions is critical for future exploration and potential colonization efforts, which we will likely do because our Earth is quite hot. And most of you may know this, but it was the hottest day on Earth as of Monday. And the record was broken on Tuesday, which is quite crazy. There were 2 world records broken consecutively 2 days in a row. So that is certainly something to keep in mind when it comes to climate change. Now, very cool stuff. Lunar seismology. Moonquakes, or seismic events on the moon, have provided fascinating insights into the lunar geology and have yielded very intriguing discoveries. So some of the cool facts about the recorded moonquakes are as follows. Moonquakes can be categorized into 4 main types: deep moonquakes, shallow moonquakes, meteorite impact moonquakes, and thermal moonquakes. So the deep moonquakes occur approximately 700 kilometers below the moon's surface and are thought to be triggered by tidal forces exerted by the gravitational interaction between the Earth and the moon. Second, shallow moonquakes have epicenters located closer to the surface and are believed to be caused by tectonic activity or thermal stresses within the moon's crust. Third, meteorite impact moonquakes have been induced by the impact of meteorites colliding with the moon's surface. So they generate powerful seismic waves that provide valuable data about the moon's structure. Lastly, we have thermal moonquakes. So lunar temperature variations, particularly during the lunar day and night cycles, they lead to thermal expansion and contraction of the moon. So this results in smaller scale quakes known as thermal moonquakes. So some surprising discoveries that moonquakes have revealed. Moonquakes can last for an extended period of time, with some seismic activity lasting for days, and some shallow moonquakes have been observed to have repeating patterns, suggesting ongoing geological processes. The analysis of seismic data helped estimate the thickness of the moon's crust, which is believed to vary between, I would say, approximately 30 and 40 kilometers. So that's 18 to 24 or 25 miles in thickness. Some more very interesting topics include seismic network expansion. So the planned Artemis program by NASA aims to return astronauts to the moon and establish a sustainable lunar presence. So as part of this program, new seismometers will be deployed to expand the lunar seismic network. This enables a more comprehensive understanding of moonquakes and provide valuable data for future lunar exploration and potential resource utilization. Next, we have the implications for lunar science. So study is our understanding of the moon's geological evolution and the presence of subsurface structures and the potential for resource extraction. So again, this is very vital for future missions, lunar-based planning, and potential human settlements. Coming up next, it's called Asteroid Seismology. So the first confirmed asteroid seismic event was, I believe, in 2021, and scientists reported the first confirmed detection of a seismic event on an asteroid. So the event was recorded by NASA's InSight lander on Mars, which picked up the seismic waves produced by the impact of the Mars InSight mission's heat probe on the surface of the asteroid known as 16 Psyche. That's Psyche. And this landmark event marked the first direct evidence of seismic activity on an asteroid. Also, we can study these asteroid interiors. So seismic waves generated by impacts, internal fractures, or other geological processes provide information about the internal structure of asteroids. So by analyzing the characteristics of these waves, we can infer details about the size, shape, composition, and even the internal layering of the asteroid. And we can also differentiate between solid and rubble pile asteroids. Asteroids come in various forms, including solid bodies and rubble pile structures held together by gravity, solely gravity. Seismic studies can help differentiate between these types by examining the propagation and attenuation of seismic waves. So this knowledge is crucial for understanding the formation and evolution of asteroids. We can also characterize asteroid impacts. So seismic monitoring of asteroid impacts on celestial bodies such as the moon or Mars can provide insights into the properties of both the impactor and the target body. So by analyzing the seismic waves generated by such impacts, scientists can study the energy released, the depth of the impact, and the resulting structural changes. Also, something really cool that NASA has been working on for quite some time right now, at this time, is planetary defense. And this is something that a lot of people do want to go into because it sounds really cool, and it is as cool as it sounds. So by understanding asteroid seismology, and this has implications for planetary defense efforts. So by characterizing the internal structure and composition of near-Earth asteroids, we can assess their potential threat and develop strategies to mitigate the impact risk. Next, we have Python implications, applications in extraterrestrial seismology. So Python is extensively used by NASA and other space enthusiasts for analyzing extraterrestrial seismology data due to its versatility, ease of use, and the availability of specialized scientific libraries. So here are some ways that Python is used. We have data processing and analysis. So Python scientific libraries such as NumPy and Pandas are leveraged to process and analyze these seismic data that are collected from extraterrestrial missions. And these libraries offer efficient data manipulation capabilities, statistical analysis functions, and tools for handling larger data sets, allowing researchers to extract insights and patterns from the data. We can also perform seismic waveform analysis, which is something that I am currently doing as well. Python, along with libraries like OBSPy, enables analysis and visualization of seismic waveforms. So researchers can read, filter, and process waveform data using array manipulation capabilities. And additionally, Python's plotting libraries, such as matplotlib and plotly, aid in visualizing seismic waveforms and extracting meaningful information from the data. We can also perform seismic event localization and characterization, machine learning and pattern recognition, many different types of data visualizations, numerical modeling, and collaborative and open source development, which is very important in geoscience, where Python's collaborative and open source nature promotes knowledge sharing and collaboration among researchers and space enthusiasts. And projects and code libraries are often shared publicly, allowing for community-driven development, code reusability, and continuous improvement in analyzing extraterrestrial seismology data. Next, we have data processing and visualization. So in the data processing section, we have pre-processing, which is the raw seismic data that is collected from the missions, often requires pre-processing to remove noise and correct for instrument responses and align timestamps. So Python offers functionalities to pre-process and clean the data, ensuring its quality and reliability for further analysis. We can also perform signal analysis. So Python also provides tools for signaling processing, allowing for researchers to analyze and extract relevant information from seismic waveforms. And techniques such as filtering, Fourier analysis, and spectral analysis, wavelet transforms, all of these things can be employed to characterize the properties of seismic signals and identify distinct features. In terms of the data visualization, again, we can do waveform plots. So these plots display amplitude and time domain representations of seismic signals, spectrograms. They are also created in libraries such as matplotlib and provide time frequency representations of seismic signals, helping to identify the frequency, content, and temporal variations in the seismic data. Event location mapping. So this is the magnitude information, the spatial distribution of the seismic events, and the geological features on maps to gain insights into the patterns of seismic activity. And there's a whole ton more that you can do, including animation and time-lapse visualization. It really does not stop there, and there's so much that you can do, which is why when you go into geophysics, you tend to get some training in these seismology, computational seismology interactions, and it's very important, especially when it comes to graduate school, when you need this kind of background information to work with professors on these topics and further your knowledge on data processing and how you can benefit the field of seismology from beyond Earth. Lastly, we have signal processing and filtering. This includes noise removal, Fourier transforms, filtering, time frequency analysis. Again, all of these are very essential techniques in extraterrestrial seismology to extract valuable information from seismic waveforms and remove unwanted noise. And we also have something called waveform envelope extraction. So the envelope of a seismic waveform represents the amplitude variations over time and provides insights into the energy content of seismic signals. So Python's signal processing capabilities, combined with techniques like Hilbert transforms and bandpass filtering, these enable researchers to extract and analyze the waveform envelope, aiding in the detection and characterization of seismic events. We now have computational modeling and inversion. So inversion is a computational technique that aims to extract information about the subsurface properties of a body by comparing observed seismic data with model predictions. I will be talking a little bit more about this when I discuss the research that I do, because I work with moment tensor seismic inversion, which is quite a mouthful, but it essentially is the creation of plots and graphs that are visualizations of the seismic events that occur on Earth into something that most people can understand, and it is very readable. So it's not something that's just numbers. And inversion helps researchers to infer the internal structure, the composition, and properties of these bodies by observed seismic data with model predictions. So it aids in refining and updating numerical models, improving our understanding of the subsurface conditions. Also, we have forward modeling, which refers to the simulation of synthetic seismic data using known equations. So Python allows us to perform forward modeling by numerically solving wave equations, such as the elastic wave equation, through finite difference or finite element methods. Again, this is beyond the scope of what I would like to discuss today, but something that I would briefly like to touch on is the uncertainty quantification, which the computational modeling and inversion also facilitates this method, which involves characterization and quantifying of uncertainties associated with the derived subsurface properties. So Python libraries like PyMC3 offer tools for probabilistic modeling and sampling, enabling researchers to assess uncertainty in the estimated model parameters. So now on to the fun stuff that I have been up to. So the goal of my research is to use code to kindly made publicly available to us by the MTUQ team at Princeton, that's MTUQ, to model and analyze the Turkey earthquakes that happened just this past February. So essentially the MTUQ package provides resources for calculations involving moment tensors from seismic data. So MTUQ has a very smart system that allows for taking in data and using that data that pulls from IRIS, which is a network of many stations with publicly available data from around the world. And OBSPy is the package that acquires the waveforms from IRIS, and PySep is the wrapper that sorts it into the right format and does quality control. So to characterize a seismic event, the moment tensor is used. It is a symmetric 3x3 tensor describing the force coupling in each Cartesian direction. And the displacement measured by each station is a combination of Green's functions and that moment tensor. And so the game that is played is to figure out the original moment tensor based on the displacement and what we know about Green's functions. So we have everything laid out for us. It's just the creation of that beach ball kind of thing that you're seeing on the top right corner of your screen. That is a beach ball, or the moment tensor of that specific earthquake. This is from the 7.8 magnitude earthquake that happened in Turkey, as you can see on that map. And if you look at the bottom left, or bottom right of your screen rather, you will see the waveforms that that line up almost perfectly. We're still working on the data and making sure that the waveforms fit, but it's essentially looking at the observed data and the perspective data, and if they align, and we're trying to make that align right now. And this is all really fun stuff. You can check out check out all possible origins and force sources, determine which, in combination with their associated Green's functions, best match the data for the displacement at each station. So this gives us adequate information to deduce the likely origin point and moment tensor of each individual event. So that is it for my presentation. I don't know if I'm allowed to take questions, but if anyone has any questions, please feel free to ask me. I'd be